Okay then, good morning.
Good morning.
I'm Anthony. If you don't know me already, then I've been a consultant for many years. I wrote C Concurrency in Action. Currently I work for Woven by Toyota, developing car software. But today I'm going to talk to you about designing for concurrency using message passing. So I'm going to divide that into 4 parts. We're going to say, firstly, why would we use message passing rather than anything else when we're designing for concurrency? Secondly, I'm going to talk a little bit about message passing frameworks and what they will do for you. And then some design guidelines. And then finally some examples. So why would we use message passing? Well, the hook, the big reason, is because it will eliminate all your concurrency bugs. That's it. No, we're done. Yeah. No. The reality is that that's not quite true. You can eliminate explicit synchronization because the message passing framework will take care of that for you. So in your code, you don't put any reference to any locks, mutexes, condition variables, anything. You just leave that to the framework. So there's no explicit synchronization in your code, which therefore means it's simple. You can also eliminate OS-level deadlock. Because you're not directly manipulating mutexes and things like that, then you're not going to encounter the basic problems of locking 2 mutexes in the wrong order and therefore deadlocking. So straight off, we're eliminating bugs. And if you do it properly, then likewise you eliminate data races because you don't have any shared state that you're then accessing from multiple threads. You keep your state isolated, you do the data transfer with message passing, eliminate data races. That's more bugs gone. This is great. But there's a cost. In exchange for these nice bug elimination benefits, you've got to do some things. And the first is you've got to actually rely on the framework for synchronization. If you start doing synchronization outside of whatever message passing framework you've got, well, then you've just introduced manual synchronization back into the mix and you've got all your bugs potential back again. So don't do that. Make sure that you use the framework and the synchronization that it provides to do your synchronization for you. And secondly, avoid the temptation for shared mutable state. If you're using message passing, then part of the benefit is that you can have separate entities that have separate state and they don't share anything except via the messages. And so if you then directly introduce shared mutable state, say by passing a shared pointer to an object as one of your messages, which is now shared between the source and the destination, then you've again introduced back the potential for data races in particular and potentially other synchronization bugs. So don't do that. Don't add shared mutable state. The whole point of using message passing really is to avoid that, to keep things isolated. And then in order to accomplish this, you often have to change your design approach. This is not the same as writing ordinary code, I say, with using locks and condition variables. It's not the same as designing parallel data processing using senders and receivers. This is its own way of designing code. And so you have to think about it as such and adjust your design approach accordingly. But we've said there's all these nice things that you can get, but there's still some potential problems. It's not a silver bullet. There is still the potential for race conditions. They're not low-level data races now, but it's things like, I'm sending messages. Which message arrives first? Does it matter? If 2 entities are sending messages to the same third entity, then does it matter which message arrives first? That's up to you to think about when you're designing your application. In some cases, it really does matter, in which case you've got to make sure that that things arrive in the right order. In other cases, then it really doesn't. And that's the ideal that you're striving for, is that the only messages that can arrive at any given point are the ones that you know about and can care to handle. And it doesn't matter what order they arrive in. But you have to design your code to get there. Similarly, you can actually design your code badly such that there is the potential for message deadlock, where two elements are trying to send messages to each other, and each of them is waiting for some form of response from the other, but they're not going to get it because they're each waiting for the response from the other. So you can still design that as into your code if you choose to do so. I strongly say don't. Because it's something that you are in control of here. But it's something to be aware of. And when you're sending messages to another entity that's then going to send something back, then you then need to pay attention to the context under which that can happen, when you might not get a response, what other messages might get in the way, and and that you might have to process beforehand and things like that. So you need to think about that in your design approach. And then, if you're using any form of message transfer which is potentially lossy, say using a network, then you now need to be aware of dropped messages. This is its own new problem. If you were not using a message passing framework but you were still sending over the network, you might encounter the same issues, but they would manifest in a different form. Because with a message passing, then from the point of view of the code in the entities that are communicating, I'm just sending a message. The fact that it's using a network transit as the delivery mechanism is now an implementation detail of the framework and not something that necessarily manifests in your code. So that's something that you need to be aware of and thinking about if you're trying to work across the network. Obviously, if everything's all on the same CPU, then the chances of drop messages is a lot lower because you probably aren't using the network. But there still might be issues, around full buffers or something if you've not thought about that sort of thing or not allocated enough buffer space in the framework or something. So, like I said, it's not a silver bullet, but it solves lots of concurrency problems for us. Okay, so that's some of the why you might choose to do this. So what are our framework going to do for us? Well, fundamentally, when I talk about a message passing framework, I'm saying tooling that manages the delivery of messages between independent elements. Now, this might be tooling in terms of a preprocessor that you run that generates some code for you, or it might be tooling in terms of a library that you link in and then you use its public API. I'm being quite general in that, and it might be some mix of the two, but that's what I mean when I say a message passing framework. And the key benefit of using a framework to do this is that then you can focus on the content of your messages, the targets of your messages, where are they going? And then, of course, the processing. When you receive a message, what are you going to do with it? And then you explicitly don't have to think about the delivery mechanism. How does that message get there? Because that's the key thing that the framework is providing for you, is the delivery mechanism. I send a message, I don't care what the delivery mechanism is beyond having configured the framework, and now it just gets there. So that's, this is what we're getting from our framework. And typically it allows you to divide your code up into entities, I called them earlier, microservices, another thing. Sometimes people might use the term actors or active objects. Now, all these things are variations on a theme, but fundamentally they're discrete units of code which you can reason about in isolation that then send messages to other discrete units. And then the API that such a microservice exposes is really just the messages you can send to it and then what messages it then produces in exchange. So one key guarantee that you might look for from your framework is that each microservice will only process one message at a time. And this is really the part that provides us lots of our concurrency safety. Because if you're only processing one message at a time, and the framework is going to guarantee that, and you yourselves have ensured that the state for each microservice is isolated from the state for the other microservices, you haven't got any shared state, then you now don't have any race conditions, because you know there's only the current handler for the current message is the only thing that's accessing the little bit of state that belongs to this microservice. And so you don't need to worry about synchronization, you don't need to worry about data races, you can just access this, it's single-threaded code. You might also get an additional guarantee, depending how you configured your framework, that all the messages for a given service arrive on the same thread. Now, subsequent messages arrive on the same thread as the first one. You might not do, it might just be that they have the one message at a time guarantee. But if sometimes having that, all the messages arrive on the same thread for the life of that service is an important guarantee. That still doesn't necessarily mean that it's a dedicated thread. It might be a thread that is shared with handlers for other services. But it means that then you might be able to have some form of persistent state that relies on the fact that it's on the same thread. Particularly if you're trying to integrate a message passing framework with some other framework, say like a GUI, then often you find that GUI code relies on all the GUI interactions for, say, a given window happen on the same thread. So having your message passing framework guarantee that all the message handlers for a given microservice are on the same thread means that then you can then freely interact with the GUI from that thread, as opposed to having to then delegate to the GUI thread. And like I said, you might find that services are allowed to share a thread. If they are, then hopefully your framework gives you some control over which services share the same thread, so that you can then isolate different parts. I said I work on car software for Toyota, and so sometimes then we might have highly important parts that are safety critical that we want to make sure that those only run on threads that are shared with other safety critical things and are not interrupted by somebody trying to turn the heating up in the thing or adjust the volume of the music, because we want to separate that onto a separate thread and keep things isolated. Okay, so the other thing that your message passing framework is going to do for you is that, well, really, one of the most important things it does for you is it controls the delivery mechanism. And it might give you a choice. You might have, they might provide various options that it can do. It might be in-process delivery. It might be between processes that are running on the same CPU. It might be between processes running on different nodes in a network. But depending how you configure it, it might actually give you direct control of these things. I'm going to guarantee that, that these two entities are in the same process and therefore use an in-process channel. Or you might, if it is pre-processor tooling that's going to generate code for you, then you might say, leave it up to the framework to choose how it allocates the services between processes. In which case, then obviously it's going to choose an appropriate communication channel for you, depending on the allocation choice it made. But the big thing is that what you want from your framework is that the code that you write for your microservice doesn't care what the delivery mechanisms are for the messages that it sends and receives. So that if you change the choice, or the framework changes the choice for you, your code doesn't change. The code that's actually processing those messages and sending them out doesn't change. It doesn't care what the delivery mechanism is. And this is this abstraction layer is one of the benefits from using a framework. So, of course, all this is the theory of message passing frameworks. And everybody knows that there's a difference between theory and practice. And in practice, when you actually look at the widely available frameworks, lots of them still require you to write a lot of boilerplate, particularly those that come in library form. Now, if you're trying to use 0MQ as your messaging framework, then you've got a nice messaging library, but then you have to write a lot of boilerplate to set up the threads, set up the message loop, do all the things. So if you do, that's unfortunate, in which case then you need to then abstract that, write a wrapper library yourself, or write a tool that's going to generate that boilerplate for you. Because as you work more with the message passing, you want to focus on writing the services and not on the boilerplate. So wrap that boilerplate. Make sure that you have a nice API that you can then use that's going to mask that complexity if the framework doesn't already do it for you. Okay, so that was what the framework's going to do for you, but how are you going to design your code to make this work, make this the best way to work for your code? And the thing is that when you're writing each microservice, you need to think. It needs to be focused. You want the services to have a dedicated task, a single responsibility. You don't want one that's going to handle 3,000 different messages and do all sorts of fancy things, because the internals are going to be too complex. And you're going to lose lots of the benefit, because now you've just got a single-threaded monolith. If you're only handling one message at a time, and you've got thousands and thousands of possible messages to be handling, then it's probable that you're missing out on potential concurrency, because some of those things could potentially have been done at the same time if you've got enough CPUs. But by putting it all in one service, then you're preventing that. So focus your microservice. It's got one dedicated task that it can do well. And related to that is you want them to be independent. You don't want your microservices to have overlapping functionality. If you're writing services to deal with file handling, you don't have one service that's going to process only messages for opening files and one that's going to only process messages for closing files, because you need to overlap and share data between them. And likewise, you probably you wouldn't want to have you would probably want to have those in the same service as something that was going to give you a list of files in the directory, so that there was some sort of commonality. We want to gather things so that, A, they are focused on what it is they're trying to achieve, but also that they're not overlapping with neighboring microservices. And then a very important thing about your messages is they should be value types. We don't want messages that have inherent behavior in the type itself. You're passing data as the message, not behavior. And the simpler that your messages are as blocks of data, then the easier it is to reason about the system. You don't have to worry about how they get transferred over the network. If all it is some data, then it's just like, well, serializing that to the network is then dead easy. The framework can deal with that. Whereas if you pass something that's got complex copy constructor operation, then when you serialize that over the network, then it really matters. Well, quite how did it do it? What did it do? Did it trigger the right copying when it was deserialized at the other end? And things like that. So your messages should be simple value types. They might be large. They might have big chunks of data attached. Passing a multi-megabyte image as a single message, fine. As long as it's just a unique pointer to a chunk of bytes or something, or a vector. But passing something that's got behavior, probably not so good. You also want your message handling to not block. So, if you should not, in your handler, be waiting for anything, ideally. You should not be waiting explicitly for other messages. That should be just left to the framework to schedule incoming messages, go to the handler. When the handler is done, we come back and we look for other incoming messages. You should not be waiting for other messages directly in your handler. You should not be calling blocking APIs if you can avoid that. If you feel the need in your design for blocking calls and blocking and waiting, then what's probably is that you want to split out a separate service. And eventually you might get to the point where you have a message handler in a service, and that message handler, all it does is call one blocking API and then deal with the result and return. And at that point, then you can't divide it any further. But ideally, that's the level that you want to go. If you want to have I call a blocking API, I process the data, I call another blocking API, I process the result from that, then you probably want to start splitting that up. And the thing that and have a new service that encapsulates those blocking APIs that you're trying to call. Because if you can avoid the blocking, it makes it easier for the scheduler in the framework to manage the work between the different threads. Because it can farm out some work, call a handler, and then it just does some processing and comes back, and then it can call another handler for the next message, and it doesn't get stalled and potentially deadlocked because all the threads are occupied with blocking API calls. Okay. It's probably quite hard to think about message passing frameworks and message passing design without talking about state machines. Because fundamentally, when it comes down to it, then messages are events. And having a service that handles events fundamentally feels like a state machine to me. And the thing about that is that if you can model your microservice as a state machine, and this is a single-threaded state machine because you're only ever processing one message at a time, then this is a known problem. As a community, as a computer science and software development, we've known how to deal with state machines for decades. And so if you can model your message passing service as a state machine, this is a solved problem that you can then look at extra tools to deal with that, without having to then worry about the concurrency aspects. You just have a state machine that has a series of messages coming in and it generates a series of messages going out. Sorted. All the normal state machine processing can now be applied to that, and you can work out how to deal with that best for the problem that you have at hand. So that was the easy bit, the guidelines. So now let's look at some examples. The first example that we have is the classic dining philosophers problem. We have n philosophers sat around a table, and for some reason our philosophers like rice, but they don't care about sharing food with each other or even sharing chopsticks. They're going to alternate between either thinking or eating. Philosophers obviously don't care about sleeping because that's just beyond, that's earthly needs, too much more than eating. But for some reason they only have enough chopsticks for one each, which is not really enough to eat rice. And so they have to share chopsticks with their neighbors. So they all start thinking, and after a random length of time thinking, they'll decide they've done enough thinking and they'll actually want to try and eat some food. So they'll try and pick up some chopsticks, and then they'll, rather than saying, oi, who's got some chopsticks, they'll just try and pick up the ones next to each other. And if they can't get them, then they'll have to sit and wait until their neighbours have put them down again. And then after they've been eating for a bit, then they'll put down their chopsticks and then carry on thinking. And obviously, we're trying to model this in a way that avoids the philosophers just sitting there all starving, each of them holding one chopstick. And we're all hungry, nobody can eat, but we're not going to do anything. So we're going to create a bunch of actors, or microservices, as I called them earlier. And we're going to have one for each philosopher. In the spirit of not having blocking things, we're going to have an actor for I/O so that we can actually send it messages that's going to output to the world what's happening. And we're going to have a separate actor for actually timing so that we can say, well, I'm going to think for a random length of time, so I'm going to decide what that period of time is, and I'm going to farm actually managing the time out to the timing actor. And then we're going to introduce an additional actor for the server, the table, the abstract system that's going to manage the chopsticks, identify who's got chopsticks and whether or not they can pick them up or put them down or whatever. So like I said, the I/O is just really straightforward. When you receive a message, we print it out. There's nothing to it. It only receives one sort of message, and all it does is print it. So it's really straightforward. But it means that the fundamental time-consuming blocking nature of the I/O is then isolated to this one actor. And the other things don't have to deal with the fact that I/O can block and take time. You just say, I'm going to send a message to the I/O actor that I want to actually output something. Timing is a bit more involved. So you get incoming, you're going to have a time when I want an event to happen, and then you need to say, well, I'm sending a message to the timing actor. I will need to send me a message back. So you've got to tell it some form of reference, a sender of some description that's going to that you can send messages to. And it will send a timer expired message to the given target at the appropriate time. And the implementation details of this, we're going to be looking at OS level calls and things to schedule callbacks at various points. And so we want this all isolated. The timing actor is something that's going to deal with OS level timing. And nothing else then needs to worry about this. Everything else just needs to say, I want a message from the timing actor, please. So we're isolating the rest of the system from this, and then we have a focused actor to deal with that. So what about the philosophers themselves? Well, philosophers, fundamentally, we have two states we want them to be in, thinking and eating. And then we have that sort of intermediate stage where they're waiting for chopsticks because they've decided they want to eat, but they can't eat yet because they've got to pick up some chopsticks first. And in each state, then there's a particular set of messages that we might have to process and some messages that we might output. So we have a set of states. We have thinking and waiting and eating. And if we're thinking, then we might wait for a timer expired message. Having sent a message to the timer saying, set the timer. Well, then the timer's expired, we're done thinking, we'll go for waiting for chopsticks. We'll send a request for chopsticks message. And then when we get the chopsticks, then we start eating. And when we start eating, then we set a timer, how long are we going to eat for? And when the timer expires, we go back to thinking. So it's a very simple state machine. And the states just naturally flow. There's only one way you can go round. But we can model it as that state machine. So what does it look like in code? When we start thinking, we need to send a message to say, to the I/O to say, this is what we're doing, so that we can actually observe the system in practice. And then we have to send a message to the timing actor specifying how long for. So we're going to send the message to the I/O and message to timing. And that's all we do. When we enter the state, send the messages. We don't need any extra behavior. It's quite simple. And then when the timer expires, now if we look back at our state machine, we might have two timing expire. The timer, we have a thinking, and the timer expires on that, or eating, and the timer expires. So when the timer message, we get a timer message, we need to care what state we're in. Now, if we're thinking, then we're finished thinking, and now we can change to waiting for chopsticks. And so, because we're focusing on thinking, then that's what we'll leave it for now, but there'll also need to be something to do when we're eating. And so, our time has expired, and we're waiting for chopsticks. We have a hungry philosopher who's waiting, give me my food, but I can't eat till I've got my chopsticks. So, first thing it's got to do is it's got to send a message to the chopstick manager, the server, saying, can I have some chopsticks, please? No, these are the chopsticks I'm after. My chopstick on my left and the chopstick on my right. And by the way, this is me, so you can tell me when I can have my chopsticks. And of course, we're going to send a message to the I/O saying, no, this is what we're doing, so that somebody watching can see on the list and see on the output. Getting some chopsticks. We receive a message, we've got some chopsticks. We know which chopsticks they are, so we've just received our chopsticks, and then we can start eating. Dead easy. Eating is another state that has an entry processing, because we need to determine how long we're going to think for, and so we actually send that out that timing message to say, I want to, I'm going to eat until this point, and then I want to get my timer expiry. And the timing message also ought to say, pass in the actor that's the get self, so the timer knows who to send the message back to. And then in our timer expiry, then again, now we can say, well, when we're eating, if we receive a timer expiry, then we know we're finished eating. We can send an I/O message for that. And then we can return some chopsticks. And then we can go back to thinking. It's all simple handlers for a simple state machine. The server actor that's managing the chopsticks has to deal with identifying whether or not they're free or not. So when it receives a message from somebody who's requesting some chopsticks, then we're going to need to check, are the chopsticks available based on the request that we've got? If they are, then we're going to say, yes, these are now used, and to notify the appropriate philosopher that they can have their chopsticks. Otherwise, we're going to need to say, well, that philosopher can't have his chopsticks yet. So we need to put that request on the list. And then on the flip side, when a philosopher is done with the chopsticks, then we need to mark that the chopsticks are available, and then we can go through our waiting list. And for each philosopher on the waiting list, we can check if they can have their chopsticks, and if they can, then we can mark the chopsticks as used and notify them that they can have them, and then remove them from the waiting list. Otherwise, we just keep going through the list. But obviously we only need to do this processing when we get a message saying somebody's given some chopsticks, because there's no point keep checking periodically just on the off chance. We know that the messages come in, so we know that the chopsticks are free. And so in both those places, then we had this use chopsticks and notify function, which is just very simple. Mark that the chopsticks are not free anymore, and send out a message to the appropriate philosopher to say, here you are, mister. You can have the chopsticks you requested, and so you can get to eating now because you've got the chopsticks. Again, it's all simple code because it's a fundamentally simple state machine. But we have a question anyway.
Everything you've shown so far happens on a single thread, right?
Maybe, maybe not. No, the whole point is that it's abstracted. Each philosopher will work on its own thread, but the whole point is that the separate philosophers could be on separate threads. The I/O on one thread, the timing on another thread, the server on yet another. So it's all abstracted and you don't need to worry. Dining philosophers, suddenly very simple. We have our messages and they all just work, and it neatly scales up for any value of n. And obviously you can put more complexity in there if you wish to. When I've done this as an exercise with students, then sometimes they add sort of, well, if philosophers have been waiting for their chopsticks for a certain period of time, they get priority over anybody else who might want chopsticks and things like that. So you can add extra things to the model, but it's very easy to do so because everything is separate and isolated. So my next example is a robot control system. If you're thinking of you have something like a robot arm, then see if it's very straightforward and it only has one motor and goes up and down, then it's not very tricky. But by the time it's got multiple motors and grabs on the end and can move in multiple directions, then there's lots to do to control it and move it to a given position. You might have multiple motors, multiple actuators that all need carefully controlling. And we want the control signals for each bit of hardware to run on its own thread so that it can focus on the timing and the control and the sequence of instructions precisely for that control piece of hardware. And another thread over here can control a piece of hardware for this other motor. And if you have a complex robot with hundreds of motors, then that can be very important to make sure that the timings are isolated, because trying to do that all on one thread is really tricky, and trying to make sure that you've correctly interleaved all the instructions to the different bits of hardware and with the appropriate timings, it's really tricky to get right. So being able to separate things out makes it much easier to think about. And so we can then have an actor for the central coordinator that's going to work out which motor needs to run for how long, move to which position to get the robot in the position we're wanting. We're going to have an actor for each bit of hardware that's actually going to control part of the robot, each actuator. And then we're going to have a separate actor for doing the timing. So we can say, well, after 30 milliseconds, then I need to stop and get a message to say that I've stopped, or I need to start moving the next bit, or whatever. So we can have all these separate actors. So if we want to move the robot to a particular large-scale position, then the coordinator is then going to gets a message to say, move the robot to position foo. And it's like, okay, well, I need to, currently the robot arm is folded up over here. I need to move it over there. How do I need to move the motors, set the positions on each of the different controls to make it work? And so you say that you change the state of our state machine. We're waiting for moving to position foo. We then send controls to each of the actors controlling each of the bits of hardware to say, move to the appropriate position. For actuator 1, we want the position for actuator 1 for the foo position at the target time. And for actuator 2, we want to be at actuator 2 foo position, again at the target time, because it might take different amounts of time for each motor to move, or you want to set different speeds, and the point is we want everything to be in the right position at the same time. And so you might say, the particular actuator hardware might say, well, I know that it takes 3 milliseconds to move to that target position, and my target time is 2 seconds time. So I don't need to start yet. But from the point of view of the coordinator, it doesn't matter. You don't need to know that. You just need to say, controller for this bit of hardware, I want you to be in this position at this time. And then the hardware controller can work out how best to do that. So we want our robot arm to be over here. So we send commands to each of the controllers saying, at the given time, please be there. And the hardware, each actuator can then do its thing. So like I said, your hardware might have specific, actuator might have hardware-specific code. It might send, if it's a very simple motor controlled thing where the actual controls that you have are turn the motor on or turn the motor off, and then you move it for a certain period of time, but you can measure where it is. You can measure physically how far it's moved along its scale, but you can't set that by hardware. Then you might say, okay, first we're going to stop moving. I mean, wherever you are at the moment, Mr. Robot, stop that motor in that position, work out where it currently is, how far it then needs to go, and therefore how fast it needs to go to get to its target position at the target time. And so then we start moving at the right speed. We send a timer request to say, to the timer actor that's going to tell us when we've been moving for the right amount of time. And then our actuator code is going. And then when the timer expiry, as it should be, timer expiry message comes, then we will stop moving, and then we can send a message to the controller saying, well, actuator 1 has reached the position that you asked it to. And the controller doesn't need to know that that's how this particular actuator works. It just needs to know, I asked you to be in the position at a given time, and now you're telling me that you've arrived at the target position. And that's all that needs to matter, all that the coordinator needs to know. Whereas the actuator needs to know that that's the control that it has over this particular motor. Obviously, different bits of hardware might have different levels of control. You might have one that's controlled by a pneumatic pump, and actually you can very explicitly set it must have precisely this pressure inside the pneumatic cylinder, and the fill time will be so many milliseconds, and so we can just set, please set the pressure to whatever. And obviously the hardware.stop moving encapsulates a lot of, it might be a whole series of USB commands or whatever to the appropriate bit of hardware. Or I2C or whatever your low-level protocol is. But again, this is isolated to this specific actor. And if that blocks, then it doesn't matter because the rest of the system is isolated. So we've looked a bit about simple positions. Okay, you want to set your robot arm over here in a particular position. But if you're actually trying to use your robot for doing anything useful, then you probably don't want to just send it to a particular position. You want to move it through a particular sequence. And so then you're likely to have potential intermediate states. It might be that even in the simple things, it might be your robot arm starts up like this and you want to move it over there, but you can't just do that as a single thing. Firstly, you have to extend it and then rotate it because of the physicality of the system. And so you want to be able to set up the sequence that says, well, first I'm going to extend it over there, then I'm going to move it around to here, and then I'm going to close the grip or bend it, lower it down, or whatever the appropriate actions are. So you have this intermediate sequence of steps. And so you just add extra states to our state machine because that's what we've got. We've got a state machine here. So we add extra messages for setting the appropriate intermediate positions and then send extra messages to notify when they've reached, even if these messages are just coming back to the same controller or changing the internal state directly. So we look at our bigger state machine diagram. We might have an idle state where the robot's not doing anything. We receive a message to say we're going to trigger sequence, our sequence 1, and the first step is, and that is going to be waiting for position 1. It's going to send messages set position 1. We're going to send messages to the actuators to set the right positions. We're going to wait for the actuators to come in as we receive the individual messages from the individual actuators saying that they've reached the target positions. When we've got all the actuators in the right message to say we're over here in position 1, then position 1 has been reached and we can change to waiting for position 2. And again, we send out messages to all the actuators, and we're going to move the arm over here. And again, I haven't put them on, but we're going to have individual messages coming back from the individual actuators, so say that they've reached the position for that bit. And again, the coordinator itself is not doing any waiting explicitly. It's just in the state that is called waiting. And when it has received the appropriate sets of messages, then it can then move on to the next state. So all the waiting is then controlled by the message framework, the scheduler of the system. And the timing is controlled by the timer actor that interacts with the OS timing facilities. So we have moved to the position, and then finally we moved to the final. We wait for the final position. When we reach the final position, then we send out a message to say the final position has reached. Sequence 1 is complete, and we move back. We're back in the idle state, though again now the coordinator knows what position the robot is likely to be, and therefore. It might be that then you actually want a different state for that now, depending on how that relates to your system and what other messages you might have. But alternatively, yes, you can just go back to idle and say, well, I have successfully moved over here. And so now we're going to think about how to move somewhere else. When we next receive a message giving us an instruction of what to do. So what does that look like in code? Well, we get a message, trigger a motion sequence. We're going to work out what the time is. We have some constant in our code that takes how long it's going to take us to get to that position. It might be that you have to calculate it based on where you currently are. And then having calculated that deadline time, then you say we're waiting for position 1, and well, in this case, I've modeled it as sending yourself a message, but you could just internally set the state directly and then have an on-state entry type processing. And then as each actuator reaches the position that you've set, then the coordinator needs to say, well, what is its current state? If we are waiting for position 1 and the actuator 1 has reached the position, then we can say, have all the actuators reached the position necessary for position 1? And if they have, then we can send out the message that position 1 has been reached. And then there will similarly be similar chunks of code for the other positions that you might have in your state machine, that your robot might intend to try and move to. So you might have this, because you might have the same set of messages coming in: actuator 1 reached, actuator 2 reached position, actuator 3 reached position. But for each of those, then what that means in the context of your robot depends on what state the robot controller thinks it's in, and what it's going to do next. And obviously, whether your state machine is encompassed by a switch statement here, or whether then you do something else to structure your code, well, again, this is state machine handling design rather than about the message passing itself. But so, again, when we've reached the whole robot is in position 1, then again we work out how long is it going to take to get the whole robot to position 2. We set our state. We start moving to position 2. And then similarly, we send out all the messages to all the individual actuators, say, move to the target position for overall position 2, and so forth. So though this was conceptually simple in terms of what we were doing, then even with three actuators and multiple positions, then actually the code was getting a bit long and complex. So if you were looking at a real robot with actually many useful positions and sequences that it might go through, then your state map is going to get really large. And so you probably want to do some form of table-driven state machine or something. And again, using all the normal techniques that you would use for managing large state machines and making sure that your state machine transitions are coherent and targeted and have defined semantics about what the different possible transitions are and things. But this is just classic state machine processing that we can look up textbooks on how to do this. And there are libraries for dealing with state machines that are readily available. And because all this, the controller itself is on a single thread, or near enough that it doesn't matter, because it's only processing one event at a time, then we can just use all the classic state machine techniques that have been around for decades. So that is just something that we can do, and the framework isolates us from the fact that we want the controller to run on a separate thread from the actuators, and that there's therefore no cross-thread messaging happening. We don't need to worry about that. It might as well all be running on a single thread, as Victor asked. Is it running on a single thread? Well, yes, it could be. And from the point of view of the system, it doesn't matter. And in fact, that's one of the things that you can do when you're testing this, is that you can potentially tweak your framework and change the settings, say, run everything on the same thread. And it will take longer, and your timings might be a little bit off. But overall, the system will still have near enough the same behavior as if suddenly it was running everything on a bunch of separate threads. So the code itself that you write for each handler doesn't care. And that's very important, one of the key benefits that we get here. Okay. So fundamentally, when we're looking at our message passing framework, then the big benefit that we're getting is that we are separating the processing and content and management of the messages from the delivery. The framework is taking care of delivering things, managing the necessary synchronization to do with that, and any network traffic, shared memory, whatever functions are called. The framework takes care of that for us. Possibly we have to write some boilerplate wrapping libraries, but we do that once, and then that's done. And then we can actually write each of our microservices or actors where we're focusing on just the messages and where they're going, what they're doing for us. And consequently, we've eliminated explicit synchronization from our code, because the synchronization happens in that delivery step that the framework is taking care of for us. So each microservice can focus on just one task. We have one task to do, we can do it well, and make sure that we focus our API on just what are the messages that we're going to process, what is the objective that we're trying to achieve, and how do we do that? What messages are we going to send to make that happen? And we want to avoid the overlap between our microservices, as I mentioned earlier. Then, if they have too close responsibilities, then there's too much interaction between them, and they can trample on each other's toes, as it were. So we want to make sure that the not only are they focused on a task, but it's a sufficiently coherent task that we don't have an adjacent microservice that does something too similar. Maybe if you find that that's happening, then maybe you want to combine the two, look at what the differences are, what the commonalities were, why was there that overlap. Our messages should be value types, something that you can just serialize and send over a message or dump to disk or store in shared memory without having to worry about internal pointers and whether or not they all line up and things. Because if it's a pure value, then you can just have the framework can deal with all that. Whereas if it's if your messages have behavior in and of themselves, then how they get copied in and out of buffers suddenly is important. And again, replace the blocking calls with separate microservices, because that is that non-blocking, having the handlers for your messages not block is an important part that lets the framework schedule things nicely and avoid and helps us get to that no deadlock scenario, because we don't have the case where the threads are all if your framework has a thread pool and all the threads are blocked on API calls, then no work gets done until those API calls return. And so we want to avoid getting that scenario by and so if we can replace all the blocking calls with dedicated microservices, we can then give that service its own dedicated thread. Say, this service makes blocking calls, therefore it needs its own thread that will only run that, and therefore it doesn't prevent anything else making progress. And so that's an important aspect that you might need to set up in your framework. But by moving it to just the one service, so the timer service that we've had in both the examples needs to make OS calls that deal with timing. Some of those might actually require that the handlers are a bit more involved than just direct process this message, send that API call, and then return. And so having that as an isolated thing then means that the rest of the system can keep processing. And then when we get to this point, then we can have each microservice can be modeled as a single-threaded state machine. And as I've said a few times, single-threaded state machines are something that as an industry we know how to do. You can just read a textbook on that, download a library, and it's potentially tedious work if your state machine is large, but it is something that you can just do and process and work through. So those of you who haven't seen it before, this is my book. So I have a couple here if anybody wants a copy. Do we have any questions? I believe we've got plenty of time. Yes. Can someone pass the microphone over?
So I am a big user of message passing in general, and I believe it's a great paradigm. But the number one issue I run into is you essentially have a queue between your different actors, and so you might run into a situation where you produce faster than you can consume, and different ways you can deal with that is that you can block the producer and slow it down, or you can give feedback and back off. But I find that many frameworks tend to ignore that problem. Some of them, just buffer stuff into memory until everything blows up. So what do you think is a correct way to handle this kind of problems?
Okay, yes. So I mean, that can indeed be a problem if your systems services are developed separately with different, and one of them they're just producing messages because as they run. And so there are a couple of ways of dealing with that. One is that you if you configure you can potentially configure your framework to drop messages if there are too many. And see, it sounds like your framework doesn't have that option, and that it just keeps adding to the buffer until you run out of memory or whatever it was you said. The second is that you can have something, you can explicitly add to your protocol something about, to control the speed of sending messages. So you can say, well, I would be ready to send a message now, but has enough time elapsed since the last time I sent one? And therefore, is it okay for me to send another message? So that actually in the producer, it has some sort of control over how fast it does, and some form of throttle. But by explicitly putting that in the API, so you can receive a please throttle your production type message, then you can allows you to design your code around that, around the fact that you might need to adjust for different recipients that can read at different rates. Another option is that you insert an extra actor in as a recipient that runs as fast as the producer can produce and then does the throttling. And so it will keep reading messages, but I'm only going to send one out every 10 milliseconds, even if I receive them every nanosecond. And so it just receives the messages and then does some form of filtering or and decimation to divide down targeted to the consumers. And if that again, so that fits nicely if your producer has a reason for why it produces at that rate and you don't want to put the throttling in there. Then you can put in a decimation filter that reduces the rate of messages and things like that. So there are options, but yes, and it is something to be aware of is whether the handlers can keep up with the producers. And again, it depends on how your framework is, because if your framework is such that the messages are guaranteed to be delivered fairly directly, then you might find that even on something that's producing really fast, then it just means that the consumer runs more often. Whereas if the consumer actually takes time to process that message so that it can't run any faster, then that's when you really do need the throttling. So I hope that gives you some options to think about.
Thank you.
So what message passing framework do you use, and which one would you advise people to use?
So at Woven, then we use one that we developed in-house. So sorry, you can't use that until our software is ready, and then you can buy the whole system as a whole. But previously, then I've used I've used ZeroMQ, which works really well. But like I said, there's a lot of boilerplate that you have to write to make it all work, and that therefore you need to wrap behind your own library. And there are particularly around setting up the queues if things are running cross-process or cross-network, then actually getting the queues set up at the process startup can be a bit of a pain. But once you've got code to do that, you can put it in your library, and then you don't need to think about it again. So, for toy examples, then there's a framework in my book that you can use for experimenting and try things out. And then there's other things. There's one called the C++ actor framework or something like that, which I haven't used myself, but looking through the examples, it looks really, really nice to use. So it's worth checking out to see whether it meets yours. I mean, there's also things like nanomessage and stuff, which are based on ZeroMQ, and people who didn't like it and produce their own stuff. So there's quite a few out there.
Thank you. Hi, Anthony. That was a brilliant presentation. Thank you. It really resonated with me. I'm kind of interested in the sort of the design phase. I mean, when you've got because you put up some really interesting state transition diagrams and stuff. Is there any sort of formal checking you do at that stage to, make any sort of semantic guarantees that stop you having problems later on, or is it just the process of developing, like a state transition diagram rigorous enough?
Well, so yes, I mean, there are things you can do when you're developing state diagrams. Then, for simple things, then you can check it over manually yourself. As you get more complex, then, like I say, there are libraries and tools that deal with state machines. So there might even be one in Boost about building state machines and things. And there's lots of things where you can do. You write a state machine table in your code, and that then, the library, the way that it processes the table, will then, can then generate an error if there's a problem and there's transitions that aren't covered and things like that. But overall, then yes, I mean it's about thinking through and making sure that you've covered everything. But because it's single-threaded and it's just, well, when this event comes, what do I do? Then it's much easier I find it personally much easier to think about conceptually, rather than trying to deal with the interleaving between, well, this thread does that and sends a message and puts a value in that, and this other thread needs to deal with that. Well, it's like, well, this thread is receiving messages and it receives this message, what does it do? And so I find that relatively straightforward to think about. But yes, for complex things, then you need to do a table-driven thing and have the tools that can deal with those tables.
Brilliant, brilliant. Thank you very much.
Right, so it seems like this is it'd be a very small step to go from this to something like what Martin Fowler calls an event sourcing model, where you capture all the messages as they occur, and then you can replay them, log them, run them in a process in debug mode, all kinds of things like that. I'm just wondering whether you've worked on services that take that extra step.
So yes, I mean that's something that yes you can do in terms of if all the messages between your services are going through the message passing framework, then the message passing framework can indeed log them and capture them and record them and then potentially replay them later. And that can be actually a great benefit from a point of view of designing a system. If something goes wrong, if you can run the system, and if you're running it in production and you actually have the logging on and it captures everything and something goes wrong, then you can say, what was the sequence of messages that led up to the failure? And then you can look at that and then you can replay it in development and do that. And that can be a big benefit. And so
actually replay it into the debugger, and you can run with G flags and everything. And,
yeah, that's right.
Even if in production you didn't have all of that set. It's a really nice.
Yes, so yes, I mean that is something that can work really well. And in terms, so there's a lot of potential there. Whether the difficulty with doing so is about where you put the isolation boundaries, because you can't. If you start replaying the system, then you're injecting messages into the code, which is now going to send new messages. And unless the new ones exactly match the recording, then you've then got to work out what to do. And so at some point, you would tend to divide your system into two parts. You have the part which you're simulating, and then the part that's live, as it were.
Ensues from that event.
And then you watch, and then you see the differences of the messages that come into the simulated part from the live part versus what was recorded, and see whether there's anything significant there, things like that. So.
Yeah, thank you.
Okay, Chris.
Thanks, Anthony. It's sort of slightly leading on from that. Yeah. What sort of experience have you got with validating state machines and doing testing? Because doing this is one thing, but we have a situation where we have quite a big system and we really need to validate that the state machine design has not got any holes. And rather than doing a full system integration test, what experience, what thoughts have you got about the sort of testing and validation?
Yeah, well, yes, testing and validating state machines is very important. And as they get complex, then it gets harder. But the tools that one uses for processing, like I said earlier, then there's, if you've got some form of table-based state machine framework, then it's much easier for the framework to be able to tell you whether or not there's transitions that are missed or states that you can't get into or can't get out of, and things like that. So look at your state machine tooling and see what support that it provides to you, whether there's something that you can leverage there that can help you with that.
Well, I actually have three things. Well, first, one with the coroutines. Well, microservices are state machines, and Core will tell you that coroutines were made for state machines. So that is actually a perfect match. You just have to co-await your message receive. And if your framework doesn't give you that, Dietmar can write that for you in half an hour. For me, it would probably be half a day, but it's not really a big deal. My question is actually if the message sending blocks, that would not be an MP framework for you. Is that correct?
Yes, if the message sending blocks, then that's something that you need to be aware of. And obviously, the way that the framework itself will know whether the sending blocks or the sending doesn't block, and because that's part of the framework. And so, in some aspects, then calling into a handler that then blocks. If the only thing that it blocks on is the send, then hopefully the framework can deal with that. But yes, if you're worrying, particularly if you're worrying about real-time processing and the maximum amount of time that your handler is going to take and things like that, then even having a blocking send is potentially going to get in the way of that. So that's something that you would need to pay attention to from your framework as whether or not it can do that. And some frameworks will have blocking sends, some will not have blocking sends. You'll need to make sure that you evaluate that appropriately for your use case. Yes. So good point. Thank you.
And my last question is, well, you said twice you really want to have value types as messages.
Yeah.
And I was thinking about, well, what if you move your message around and each single microservice adds to that specific object?
Yeah. Well, I mean, then the object is if the object is still just data, so you can pass it around, then yes, you can add to the data and pass on that chunk, but now it's a chunk with extra bits, and then you process it somewhere else, and now it's a chunk with more bits, and that actually maps to Bryce's example from the keynote yesterday, where he was doing his inclusive scan, and that was then accumulating in the data that you were passing around, but that the data itself, it was a vector that was being moved, or a span that was just being passed as a raw span by value. And so, yeah, that is still a value, but it's a value that's accumulating data, and that doesn't seem at odds to me. So
yeah, but of course, instead of doing all the work in the microservice, you could also have the member functions in your message type and just run those member functions in your
you could, and at some level then that would work, but the reason why I emphasize that you want value types is because then the framework is free to move things around and copy things, whereas if you start putting too much behavior in the object, then it becomes the object has identity and now it matters whether you copy it and what you do with it. Whereas if it's just a vector and the operation that you're doing to it is pushback, then it's still a value, really. Whereas if you're giving it a more complex operation to do, then it starts being something that's it matters that it's that object rather than that other one, and then the lines get blurred. And it's much easier to deal with if you stick to values, and quite where you draw that line in terms of operations that add some data to something, I guess is up to you. But yeah, from a conceptual point of view, then what you don't want the identity of the object to matter if you're trying to have the framework manage the delivery, because you want it to be able to serialize it or deserialize it as appropriate and not worry about what happens as long as the data's the same.
Okay, so you really want something that is copyable, so something that would be move only would probably break with a lot of frameworks.
with a lot of frameworks, yes, it would break. No, there certainly are frameworks where it would work if it was moved, particularly if you're entirely in process. But as soon as you're thinking about cross-process stuff, then you need to work. You need something that is readily copyable, even if that's a serialized, deserialized operation.
Thank you.
Any more questions? Doesn't look like it. Okay, let's get some lunch.